All right, chapter 16. Believe it or not, we just keep kind of moving along here. Chapter 16, acids and bases. And as that, I hear that. It's a huge sigh of relief from everybody. Acids and bases, we've already talked about acids and bases, and we really concluded the school year in May last year in regular chemistry with acids and bases. And this first section, 16.1, is a review of that. So you should be able to take a deep breath and be like, oh man, I've learned this. I feel good. Let's do a little review. I should be ready to rock and roll. So when we talk about acids and bases, remember we have multiple definitions of an acid. First, our first definition is arrhenius. Arrhenius is any substance that increases the concentration of hydrogen ions. That's an arrhenius acid. An arrhenius base is anything that increases the hydroxide ions. So from an arrhenius perspective, we're focused on H and OH. Now let's review here a little bit. What are some qualities of acids? Remember, they start with H. They have a pH less than 7. They're used in a variety of things, foods, all over the place. They're broken into strong, weak, and organic. All right, same thing for bases. Remember, bases start with O. Typically have OH. They have a pH greater than 7. They're used in cleaners, in soaps, and dyes. All right, so just kind of refreshing yourself on what acids and bases are. Now, there's arrhenius. And there's also Bronsted-Lowry. Now, Bronsted-Lowry acid is a proton donor. That means it's giving a positive charge typically. Sometimes it's hydrogen, but it's not always hydrogen. And a base is a proton acceptor. So reviewing Bronsted-Lowry. Now, to be a Bronsted-Lowry acid, you have to have a removable proton, and to be a Bronsted-Lowry base, you have to have a pair of non-bonding electrons, which is what we're talking about as a married couple. So just kind of remember that's kind of how we phrased it, as a married couple. Now, what do you call something that can either be an acid or a base? Anyone remember? It's called amphoteric or amphoteric. We called amphoteric last year amphrotic. Amphoprotic. Ugh, I can't even spit it out right now. Amphoteric. All right? So anytime we have acid and it's dissolved in water, what's doing is it's removing the H, and water, being our base, is getting that H, and it's forming a hydronium ion. Remember, hydronium is H3O+. All right? So that's typically what's happening. Now, anytime we have an acid in water or vice versa, even a base in water, remember we're going to have a conjugate acid and a conjugate base. And the conjugate, remember, is what's left over. So when we have a conjugate base, that's the leftover of the acid. When we have a conjugate acid, that's the leftover of the base. So if we look at this example here, we started with HNO2. It gave away its proton, it gave away its hydrogen, and what's left over is the NO2, so that's called the conjugate base. Likewise with water, water's H2O. H2O is the base. It's receiving a proton, it's receiving that H, and what is left over is H3O, and we call that the conjugate acid. Acids, bases, and strengths of acids and bases. All right, we have weak acids. Remember, we have weak acids, strong acids, and organic acids. So kind of keep that in mind. Remember, there are the 7 strong acids that we need to always remember. Conjugate bases are so strong acids completely dissociate, which means their conjugate bases are very weak. Weak acids only dissociate partially in water, and their conjugate bases are also generally pretty weak. Something to keep in mind. Substances with negligible acidity do not dissociate in water. Their conjugate bases are exceedingly strong. So just something to kind of keep in mind there. H2O is a much stronger base than Cl-. So the equilibrium is so far to the right that K is not measured. It's so much greater than 1. All right. I need to focus on this. Amphoteric, as we've seen, water is amphoteric. In pure water, a few molecules act as acids and a few act as bases. So it breaks apart into our hydronium ion, H3O, and our hydroxide ion, OH. This is autoionization. Now we can study this reaction and we can kind of come up with a general idea. We've been studying Kc equations. Well, the Kc for that reaction on the bottom, since water is a liquid, is just our products, and it's H3O times OH. This is a special equilibrium constant for water. And at 25 degrees, we know that Kw equals 1.0 times 10 to the negative 14th. Now what we can do is we can take this equilibrium constant for water at this special rate, and we can solve for pH. And we did this last year. So this is nothing new. Remember that pH is equal to the negative log of H3O, or the negative log of our hydronium concentration. In pure water, Kw equals 1.0 times 10 to the negative 14th. So in pure water, H3O equals OH. We're only proving the fact that the pH of water is 7 here. So we have done this before. All right, we have totally done this before. This is something that we did last year. We're just using our equilibrium constant, our Kc, which is called Kw for water, since the water is a special exception here. So it's called Kw, and proving that the pH of water is 7 based on our hydronium and hydroxide concentrations. All right. pH scale. Here's just a general pH scale for a wide variety of things, going from 0 to 14. The P tells us that we are going to have a negative logarithm. So the P is really giving us the negative logarithm of our H3O, or our H concentration. So if you have P in another scale, you're really going to solve for the negative log of whatever is after the P. So if we have POH, we're going to solve for the negative log of the OH concentration. If we have pKw, or pKa, or pKb, you're going to solve for the negative log of Kw, or the negative log of Ka, or the negative log of Kb. We know that pKw is 14. We've proved that. We've measured pH. Last thing that we can kind of talk about is how do we measure pH? What are ways in which we've measured pH? We've used a pH meter last year. We've used the test strips. We used cabbage juice as a natural indicator. There are a wide variety of ways to do it. Now remember, last year you used 2 indicators really. You used phenolphthalein, which is the one that went from clear to pink, and you also use bromothiamyl blue, which goes from yellow to green to blue. At a change is an indicator when it changes from an acid to a base, or base to an acid. It's going to change colors. All right, we've used the pH meter, which measures the voltage. And then lastly, last little bit here, we have talked about acids and bases, but let's review one last thing in section 16.1. We have strong acids and strong bases. And remember, here are our 7 strong acids. We have HCl, HBr, HI, not the halogens minus F. Then we have nitric, sulfuric, chloric, and perchloric. Those are the 7. Those 7 are going to come into huge play here when we start figuring out equilibrium constants of acids. Remember, strong acids are great electrolytes and exist as ions in aqueous solutions. And then lastly, let's review strong bases. Where are our strong bases? Alkali metals and heavier alkaline earth metals. So anything, all the alkaline metals and all of the alkaline metals under calcium, including calcium. So strong acids, strong bases, Great review for strong acids and strong bases. So that kind of concludes section 16.1. This is just a review on acids and bases. We're talking about, remember, pH is equal to 14 when we take the concentration of H and OH. And then a refresher on the strengths of acids and bases. This concludes section 14.1.